Here's a question that sounds stupid, but it isn't. What is nothing? Not almost nothing. Not very little, I mean nothing. Empty space, zero. The void, physicists spent decades trying to answer that. And when they finally did, the answer broke physics twice, because it turns out empty space isn't empty at all. Right now, in the space between your hand and this screen, something extraordinary is happening, constantly, violently, and completely invisibly. And by the end of this video, you're going to understand exactly what and why it matters more than almost anything else in physics. Let's go back. For centuries, the picture of empty space was simple. Remove all the matter, turn off all the light, cool everything to absolute zero, and you have nothing. Pure, peaceful, silent nothing. Newton thought space was a container, a big empty box that the universe sits inside. Maxwell thought it was filled with something called the aether, an invisible medium that light waves travel through. We killed the ether in 1887, and for a while we were back to the empty box. Show a simple diagram, particles being removed from a box, temperature dropping, lights going out. The box is empty. The first principle is that you must not fool yourself, and you are the easiest person to fool. I would lean in and say, we fooled ourselves. The empty box isn't empty, and the proof came from the strangest place. A prediction that the universe itself would have to make from scratch just because of a rule called the uncertainty principle. Now here's the key idea, the uncertainty principle. Heisenberg told us you cannot know both the energy of a system and its exact timing with perfect precision. The more precisely you know one, the less you know the other. And here's what that means for empty space. The vacuum can never be perfectly still. If it were, we'd know its energy was exactly zero, which would violate the uncertainty principle. So the fields are forced by the laws of physics themselves to constantly fluctuate. These fluctuations produce pairs of particles that pop into existence, borrow energy from the vacuum, and then annihilate each other in a fraction of a second. We call them virtual particles. Now I would stop here and say something important. Virtual doesn't mean fake. These particles have real measurable effects. And we've measured them in 1948. A Dutch physicist named Casimir predicted that if you place two metal plates very close together in a vacuum with nothing between them, they would be pushed together by a force. A force from nothing. Two plates in a vacuum. Waves, virtual particles exist outside the plates but not between them. Net pressure pushes the plates inward. The Casimir effect was confirmed experimentally in 1997. Empty space pushed two metal plates together. Nothing did something. Let that land for a moment. Here's where it gets wild. If empty space has energy, vacuum energy, then the entire universe is filled with it. And that energy should have weight. It should affect how the universe expands. Einstein called this the cosmological constant. He originally added it to his equations to keep the universe static, then abandoned it as his greatest blunder when we discovered the universe was expanding. But then in 1998, two teams of astronomers, independently, both discovered the same thing. The universe isn't just expanding. It's accelerating. Something is pushing space apart faster and faster. We called it dark energy, and the leading candidate, vacuum energy. The energy of nothing, timeline. Big Bang, expansion slowing then, around 5 billion years ago, acceleration begins. Dark energy takes over. Here's the uncomfortable part. When physicists calculated how much vacuum energy there should be based on quantum field theory and compared it to what we actually observe in the universe, the answer was off by a factor of 10 to the power of 120. That's not a small rounding error. That is the largest discrepancy between theory and observation in the history of science. It even has a name, the cosmological constant problem, and we have no idea how to solve it. I think I can safely say that nobody understands quantum mechanics. So let's come back to the original question. What is nothing? The honest answer is we don't fully know. But here's what we do know. Nothing isn't empty. The vacuum is a seething, churning sea of energy and probability. Particles are born and die in it every moment. It has structure, it has geometry, it pushes things, it shapes the entire fate of the universe. Feynman had a beautiful way of thinking about this kind of discovery. He said the universe isn't obligated to make sense to us. Our job is just to look carefully and try to describe what's actually there, not what we wish was there, not what's comfortable. And when you look carefully at nothing, really look, you find that the most profound mysteries in physics are hiding inside the thing we thought wasn't there. That's not a problem. That's the best possible news. It means there's still so much to discover. If this made you curious, that's the point. Drop a comment with the thing that surprised you most. Is it the Casimir effect? The 10 to the 12th problem. The idea that fields fill all of space. I read every comment, and the best questions become the next video. If you want to go deeper, I'd recommend Feynman's own lectures, especially QED. It's short, it's readable, and it will rewire how you see the world. Link is in the description on Shima Subscribe if you want more physics explained the way Feynman would have wanted it, with honesty, with curiosity, and without pretending the hard parts are easy. See you in the next one.